Hi, grade 11s. We are starting the second unit here. So this is going to be unit 2, which is called chemical reactions. And so this is going to be lesson 2.1 for you. So 2.1. So just follow along, get the notes, and then you can do the assignment at the end. So we're just going to do a quick little review here. Now this is technically from grade 9, so I want you to draw the Bohr model for aluminum. Now actually in grade 9 you would have been asked to just draw aluminum, the Bohr model, but now I'm going to ask you to draw aluminum 3 positive, okay? So aluminum 3 plus. So hopefully by now you would know that this is now an ion instead of an atom, and because it is an ion, it has an ionic charge. And what this means is that some of the electrons have been lost. Now 3 electrons have been lost because we've got an overall charge of 3 positive here. So when I'm drawing my Bohr model, I don't want to have all the draw all the electrons. I'm going to draw 3 less. But let's go ahead and figure this out here. Now, in the middle, we've got 2 particles, right? So we've got our protons and we've got our neutrons. So hopefully you remember that the number of protons is equal to the atomic number here, so that big whole number. Now for neutrons, we know that mass, so the mass of an atom is equal to the number of protons plus the number of neutrons. So therefore neutrons is going to be equal to mass minus the number of protons. So what we're going to do, we're going to make this a whole number, right? So 27 minus 13, and you're going to end up with 14 neutrons. Okay, now we have to place our electrons. Now, like I said, normally in a neutral atom of aluminum, we would have 13 electrons. It's not neutral though. We've got a charge. So in the first one, remember, it can hold 2. The first orbital can hold 2. In the second one, we can hold up to 8, right? So I'm going to go 1, 2, 3, 4, and then we start doubling them. 5, 6, 7, 8. So right now I'm at 10 electrons, and that's where I'm going to stop because the aluminum has a charge of 3 positive, which means it's got 3 less electrons than it normally would. Okay, so exercise 1 is basically just review of these kind of concepts. So take a look at exercise 1 now then. Okay, now I want everyone to look at the periodic table, and I want you to identify, look at all the atomic masses. So what I'm asking you to do is, this is the atomic mass here, this 26.9815. So if you look at a periodic table, what do you notice about almost all of the atomic masses? And hopefully you have come to the fact that almost all of them have decimals. So did you ever think why? Remember, mass is equal to protons plus neutrons. So protons and neutrons are always whole numbers. So why do the masses have decimals? That's the question I'm asking you. So the reason for that, some of you will maybe know this already. So I'm going to reveal it letter by letter. It's an I, S, O, T, O, P, E, S, isotopes. Okay, so write down isotopes here. Some of you will have seen that maybe in your grade 10 year. It's hard to say. Now, isotopes are defined as atoms of the same elements. That means they've got the same number of protons, but they have different numbers of neutrons, okay? So they have identical atomic numbers, but different atomic masses. And you can write down those 2 definitions there. Therefore, the masses listed for elements on the periodic table are averages, okay? So they're calculated averages of the mass, because we know we have different isotopes of different atoms. And so we can use that to figure out what the average masses are. Now, isotopic notation, so again, you know this part already. Isotopic notation, we've got X here stands for the chemical symbol, and then the superscript is the mass number, and then the atomic number is below that. So you will see other things there. So for example, well, actually, I'll talk about the next example. Here we go. For an example, so these are the 3 isotopes of hydrogen. So protium, this is the one we're used to seeing, right? So the mass number is 1, one atomic number. So if we look at this one, how many neutrons does protium have? And it'll be 0, right? Because remember, neutrons is equal to the mass subtract the number of protons, right? So the mass minus the atomic number. If we look at the next one, deuterium, so deuterium has 1 neutron, okay? So it's still got the 1 proton, so I take the mass minus the proton. So deuterium, a deuterium atom weighs 2, it has a value of 2 there, because that's the protons plus the neutrons. And then we have this third one here, this tritium, which is 3 ones. So that one has 2 neutrons. So we've got 3 different versions of hydrogen, and these other isotopes are used in various research. Often isotopes are radioactive, so that allows scientists to use isotopes in a lot of different research, because if they're radioactive, they're going to be emitting alpha particles or beta or gamma particles. And at that point, then a scientist can identify them. So often isotopes will be used to show where maybe an organism is depositing certain types of elements or minerals, okay? Now, atomic mass unit. So this, you're going to see AMU, so that's atomic mass unit. Sometimes you'll see this Greek letter mu with the funny tail. Sometimes you'll just see the letter U. So that's the atomic mass unit. So 1 atomic mass unit is equal to 1/12 of the mass of a C12 atom. So this is carbon-12. There's different ways of writing isotopes, so we did talk about this notation here. So that carbon-12 would be notated like that. However, we do have also carbon-14, other types of carbon. So we can write it various ways. So you can write it as C12, C14, and you'll see, sometimes you'll see, you'll see various ways of notating this. This is sort of the standard accepted way, but there's other shorthand ways of doing it. Anyways, so we know that 1 atomic mass unit is the mass of a carbon-12 atom. So all of the atomic masses are based off of carbon. So the question is, why did scientists choose carbon to base everything off of? And there are 3 reasons for that. The first one is that it's common. Carbon is everywhere. It's in almost everything, right? In our world, any organic compound has carbon in it. So carbon, very prevalent. Number 2, it results in nearly whole numbers for most other elements. So if you check your periodic table, you will see that looking at the periodic table, most of the masses are pretty close to a whole number. The odd one isn't, but they're pretty close to whole numbers. And number 3, it results in the lightest element, which is hydrogen, having a mass of 1 atomic mass unit. So we like that as humans. We want our numbering to start at number 1. Okay, so those 3 reasons are why carbon was chosen. Now, I want you to look at this example again. So this is back to our hydrogen here. So if I calculate the masses of each of these, so this is going to be 1 AMU, this is 2 AMUs, and this one is 3 AMUs. So those are the 3 types of hydrogen that naturally occur on our planet. So you will find different isotopes of hydrogen, and these are the 3. However, if I asked you to find the average of this, so if I ask you to find the average mass of the 3, what you're going to do is 1 plus 2 plus 3, right? You're going to divide them all up and divide by how many there are, right? Which is a 3 there, which would be 6 divided by 3, which would be 2 atomic mass units. So that would be our mass for hydrogen. However, it is listed as 1.0079. Why? So think to yourself, why is the average this and not this? Now I want you to think, if you got, I'm going to put this in an example for school terms, if you got, say you got 50% on a quiz and 100% on a unit test, would it be fair if I said your average was 75% for the course? No, it wouldn't be. So why isn't it fair? This one's a quiz, this one's a test, Now, what do we know? Sorry, my marker's not working here. What do we know about tests in our class? Yeah, they're weighted heavier, right? They're more important. So looking at back to this hydrogen here, this average gives us information about how often hydrogen is protium, deuterium, and tritium. And so which one is it most often going to be? Yeah, so hydrogen is almost always protium. I think it's like 98 point something %. So it's very, very heavily favors the number one, hydrogen one. So in terms of chemistry, we call this relative abundancy data. So how often is an element that particular isotope? And we use that to calculate the average atomic mass of elements. So this mathematically is called a weighted average. And so most courses would run on a weighted average. Mine do, for example, your labs are worth 20% of your grade, your tests are worth 35%, your exams are worth 25, et cetera, right? So that's called a weighted average. So we're going to work through this example here, and we'll do that on the next page. And I always think this is funny because this is one of those things that people, if you were in a math class, you would be able to do it, but as soon as we make it real life, with elements, it becomes difficult for people, but we're going to calculate this exactly how you would any kind of class average. So, for example, 93.1% of potassium atoms are K39, 6.88% are 41K, and only a trace amount are 40K. So calculate the atomic mass. So I'm going to be calculating the average mass, and I'm using the percentages here to help me. So right away, I should note that the vast majority of potassium atoms are K39. So that means that my mass is probably going to be pretty close to 39 atomic mass units because that's the one that is most common. It's the most abundant. So how we do this, I'm just gonna set up a little chart here. So I've got K39, and that's going to be 93.1%. I've got K41 as 6.88%. And so the question, do I need to worry about K40? It says a trace amount there. Do I need to worry about it? And the answer is yes, you need to worry about it. Now, how do you find that percentage? What do percentages always add up to? 100, right? So this is going to be 0.02% is our K40. So we do need to factor that in here. Okay, so now what we're going to do, how you solve these, you're going to take the mass, which is like the 39, and you're going to multiply it by the percentage. But remember, percentages are it's actually not 93.1, it's actually 0.931. So divide by 100 for those percentages to get them into their real number. So I'm going to say mass, and then I'm going to add them all together. So 39 times 0.931 plus 41 multiplied by 0.0688 plus, and then I have 40 multiplied by 0.0002. And you can use your brackets on your some calculators don't do BEDMAS very well, so you can use your brackets for that on your calculator, but you just do the math on this, and you end up with 39.1378 atomic mass units. And so in terms of sig figs for this, we're going to use, what are we going to use? I think in some ways I just want you to keep 4 decimals here. So just keep 4 decimals, and that'll make more sense as we go through some other examples. But okay, so that is my atomic mass unit. So let's do a double check here. I said initially, right, I said that I want it close to be 39. That didn't work very well, did it? 39 atomic mass units, and it is. So I think I'm right. That's good. Okay, so the next one I want you to try on your own. So this is boron. Often we talk about these elements and we don't actually know what they look like at all, right? So this is boron. Boron's our metal here. It's quite pretty. Boron has 2 isotopes. So we have boron 10 and we have boron 11. So we know that boron 10 has a relative abundancy data of 19.78%, while boron 11 makes up the rest. Determine the atomic mass. So in order for you to solve this, you're going to have to figure out what boron 11 percentages is first, and then you're going to find your average using those percentages. And your answer is going to end up being 10.8022 atomic mass units. So I want everyone to try that on their own, and then we will discuss that in class. Thanks, everyone. You can now try exercise 1. So like I said, exercise 1 is a review. So if that's easy for you, don't even do exercise 1. That's fine. I'm really concerned with exercise 2. So give that one a try. There's one of the questions on there. I think it's number 5. Number 5 people tend to struggle with on here. So make sure you try it. See how you do. And then I don't think you have the answers for this one. No, you don't have the answers for this one, so we are going to talk about it in class, and we'll correct it then. Okay, thanks, everyone.